Hello everyone, this is Manish from Skillable India. And in today's session of geometric dimensioning and tolerancing, we are going to discuss the very important topic, which is about the virtual condition. Okay, so what is a virtual condition? In simple words, if I will tell you what is virtual condition, so this is the worst case scenario of the mating parts. It can be a hole or it can be a pin. Okay, so in this particular session, actually, we are trying to ensure that the assembly between the mating parts and we are going to calculate the sizes of the functional gauges. And if in this video we are going to ensure that the part are going to be assembled with one another. Okay, the part with the hole and the part with the pin, they are going to assemble with one another. We are going to ensure in this session. Okay, so virtual condition is the worst case condition that the part can have. Okay, so how to calculate this? We will take first of all one example. Okay, so I have already told you that the virtual condition is a worst case condition of a feature in terms of mating of hole and a shaft. Okay, shaft or a pin, both are same thing. Okay, so we are ensuring the assembly. Okay, so we are taking the worst case condition example over here. So this is the example. In this case, we have hole this side, part number one, and this is the pin. Okay, part number two. Now we have to ensure that this hole should be assembled with this pin. Okay, sorry, this pin should be assembled with the hole. Okay, to understand the boundary concept, so first of all, we have to understand what we have to understand is boundary concepts. What is boundary? Okay, so we are going to understand the boundary concept in detail. So we have to understand this boundary concept. We are going to understand with the help of this example. So here we have two parts, one with the external feature of size. So pin is an external feature of size, and hole with the internal feature of size. Okay, so this is the internal feature of size. Whenever I am using the terminology external feature of size, means I am talking about pin. Whenever I am using the terminology internal feature of size, I am talking about hole. Okay, so don't be confused in this. We are just trying to ensure that the assembly between the hole and the pin. Okay, so to understand this concept better, okay, so for both of them we have a same limit of size. Okay, so you can see that the for hole 40.5 and 40.1 is the limit of size, and for shaft also we have same limit of size is over here. Okay, so in case of hole, 40.1 will be the MMC, maximum material condition, and 40.5 will be the least material condition. Okay, in case of shaft, 40.1 will be the least material condition and 40.5 will be the maximum material condition. Okay, so this is the case for we have taken the same tolerance, same positional tolerance, which is 0.1 in both the cases. Okay, so both cases we have taken 0.1 positional tolerance. Okay, in these two parts, the worst case of the internal feature of size will be, what will be the worst case in this case? The worst case will be the for the internal feature of size will be the smallest hole. Okay, so smallest hole means the 40.1 maximum material condition. Okay, for hole. So smallest hole will be the smallest hole with the positional tolerance of 0.1. So here is the worst condition. So if we calculate the worst case boundary for this, so we will get 40.1 minus 0.1. Okay, we get 40 mm as the worst case boundary. So for hole, worst case boundary is the 40 mm dia. Okay, so dia 40 mm is the worst case boundary we have. Least material, maximum material condition minus the geometric tolerance value. Okay, so minus positional tolerance. So the the smallest hole we can manufactured with with this dimension we can have is of 40 mm dia. Okay, so this is the worst case condition for the hole, for the internal feature of size. Okay, if we take similar for the external feature of size or the pin, so what we can have is in this case also we will take maximum material condition, which is 40.5. Okay, so this is the maximum material condition for the shaft. 40.5 is the maximum material condition for the shaft. So what can be the worst case condition? That the shaft can be biggest. Okay. So if we manufacture the shaft and if we see the virtual worst case boundary, so worst case boundary will be the MMC plus the positional tolerance, which is 40.6. Okay. So in this case, worst case boundary will be dia 40.6. Okay, so the part produced by 40.6 will never enter into the hole, which is having envelope of 40 mm. Okay, so this shaft is never going to enter into this hole because the size of the size is not matching. Okay, so that's why we calculate the boundary conditions. Okay, so that's why we are calculating the boundary, worst case boundary. That's we should ensure the assembly. Okay, so in this case, you can understand. So this is where we are calculating the boundary condition comes into picture. Okay, so that's why as a design engineer, all the time we have to see that the size. If we are taking the size of the hole, so what should be the size of the pin that is going to be assembled with the hole. Okay, so we need to ensure and we give exactly that dimension that ensures the assembly. Okay, so always we try that the maximum material condition for the hole and the maximum material condition for the shaft should be same. Okay, so how it will be same and how we will calculate that what should be the worst case with the help of boundary conditions, how we can calculate the right dimension for the pin or the hole. Okay, for the internal feature of size or for the external feature of size. So we are going to understand with this. So we will again come to this example with the different dimensions. Okay, so first we will understand about the boundaries. Okay, worst case boundary, inner boundary, and outer boundaries. Okay, it is important to be able to calculate the boundary condition for a feature of size for several reasons. Okay, so it is important that to be able to calculate the boundary conditions for the feature of size for several reasons ensures that mating part will assemble. Okay, so we are here, the cost is a hole and pin should be assembled. So these both the things should be assembled. The main thing is the assembly. Okay, so we need to ensure that the pin and the hole should be assembled with one another. So in which we can calculate for the design gauges, make engineering calculations, etc. Okay, so the boundary concept in this section are explained using the example of the boundaries affect assembly. Okay, so what is the worst case boundary? The worst case boundary is a general term, okay, used to refer to an inner boundary or an outer boundary. Okay, so worst case boundaries is a general term and used to refer an inner boundary or an outer boundary. Okay, or a virtual condition. The worst case boundary affects how part will assemble. Okay, so just why we are calculating this worst case boundary, because we know the exact dimensions that to be give onto the engineering drawing to manufacture. Okay, so that's why these boundary conditions are very important. So we will one by one we will understand that is what is inner boundary, what is outer boundary, and what is the virtual condition, and what are the different effects in the virtual condition and how we will calculate them. Okay, now first thing is the inner boundary. Okay, so what is inner boundary? First of all, we will understand internal feature of size for hole. Okay, so inner boundary we are going to calculate for the hole as well as for the shaft. So for inner boundary, we will calculate for the internal feature of size or the hole and the external feature of size or the shaft. Okay, so what is inner boundary? Inner boundary for an internal feature of size or hole is a worst case boundary generated by the smallest feature of size MMC. So for hole, MMC will be the smallest hole size. MMC will be the smallest hole size. Hole size. Okay. So here in this definition, the smallest feature of size MMC minus the effect of the applicable geometric tolerance and any additional tolerance or the bonus tolerance that may apply. Okay. So in this, just it is saying that the MMC minus the geometric tolerance value. Okay, GTV. So this is the condition for the hole. So this is the inner boundary. So if we calculate the inner boundary for hole, okay, for internal feature of size and the external feature of size. So in this case, inner boundary is MMC minus geometric tolerance value. Okay. For external feature of size, inner boundary of an external feature of size is the worst case boundary generated by the smallest feature of size, means the smallest shaft. Inner boundary will be the LMC minus the effect of the applicable geometric tolerance and additional tolerance, bonus tolerance that may apply. Okay, so minus the geometric tolerance value. Okay, so inner boundary for hole will be MMC minus geometric tolerance value, and inner boundary for this shaft will be the LMC minus geometric tolerance value. Okay, in this case, you can understand that the inner boundary will be the actual related actual meeting envelope. Related actual meeting envelope. Okay. And in this case, you can see that it is related actual minimum material envelope. Actual minimum material envelope. We have already understood this concept earlier of the envelope. Okay. What is actual minimum material envelope and what is actual related actual meeting envelope. Okay. So this is the imaginary one. Okay. And this is the real one. Okay. So this is all about the inner boundary for the internal feature of size hole and for the external feature of size shaft. With the help of example, we will understand this inner boundary concept in very detailed manner. Okay. So first of all, we are taking an example of RFS concept. So in this, RFS is the positional tolerance do not have any material condition. Okay. So first of all, this is for the hole. Okay, for internal feature of size hole, we are going to understand this concept. So the maximum material condition of the hole is 40.1. Okay, and the geometric tolerance value is 0.1. So the inner boundary is equal to the maximum material condition minus geometric tolerance value. Okay, so it is going to be 40. So inner boundary for the hole is the smallest hole size. Okay. So in this condition, let's say this is the true geometric counterpart. Okay. And this is the center. Okay. With this center, the hole is being created with the maximum material condition. Okay. With the center hole, which is not possible. Okay. So one by one, we will understand that what can be the conditions. Okay. So this in this concept, you can see I will show the extreme conditions that the part can be manufactured. Okay. So we are having MMC over here 40. Sorry, MMC we are having 40.1 dia. Okay. And the geometric tolerance value we are having 0.1. Okay. So you can see that here we have an internal feature of size with positional tolerance applied at regardless of feature of size. Okay. So to get the center of the hole, we here at have the tolerance zone. So this is the tolerance zone, which is having 0.1 mm of tolerance zone. Okay. And the part is manufactured with dia 40.1. Okay. So this is the tolerance zone we have 0.1 mm and the part is produced at the maximum material condition, which is 40.1. Okay. So this is the ideal situation basically. So this is the ideal situation uh, is to have the center exactly with the true position. Okay. Which is very, very difficult. Okay. So the whole center anywhere within the circular tolerance zone. So it can be within this circular tolerance zone anywhere. It can be maximum here. It can be maximum here. It can be here. It can be here. So this whole center will vary within the tolerance zone. Okay. So in this case, the extreme top, extreme corner, extreme left, extreme uh, right. Okay. So with this, you can understand that the tolerance zone we have here is at maximum. Okay. So these are the extreme conditions what we have here. Okay. If you put all the extreme condition together, so in this case, all the extreme conditions are together, we end up with the combination like this. Okay. So in this case, if you want to assemble a true geometric counterpart or pin, okay. In this case, if you want to assemble the pin, so it will be the smallest size. Okay, so this green circle you can see inside this part. So however it is manufactured, the condition will be this, that it should be manufactured at inner boundary 40 mm. Okay, so this inner boundary will be 40 mm. So if the pin size is 40 mm, okay, it will enter into this hole. Okay, so the smallest size, the pin size should be 40 mm, then only it will enter into this hole. Okay, if it will be more than 40, maybe the chance can come it will not get assembled. Okay, so the least size of the pin will assemble is 40 mm. Okay, after all the worst conditions. So these are the worst case scenarios, that the part is manufactured at extreme conditions. Okay, so these are the extreme conditions, that the from zero point 0.1 tolerance zone. Here if the center is over here, if the center is over here, if the center is over here, if the center is over here. Okay, so these are the extreme conditions of the hole. So if the pin size is 40 mm, it will definitely get going to assemble. So this is why we calculate the inner boundary. Okay, similarly we will understand the boundary, outer boundary. Okay, so for both the conditions we will understand outer boundary for the internal feature of size hole and the for external feature of size shaft. Okay, so outer boundary is the largest feature of size LMC. Okay, so hole with the LMC, outer boundary is equal to the LMC plus the effect of applicable geometric tolerance. Okay, any additional tolerance that may apply. Okay, so in this case, you can see that the outer boundary for the hole is the actual minimum material envelope. Because if this is a part, okay, and the boundary condition is inside the material, okay, if it is inside the material, so this is an imaginary boundary. This is an imaginary boundary, and imaginary boundary we have already understood that this is the related actual minimum material envelope. Related actual minimum material envelope. Okay, so that's why these envelope is to understand in a very detailed manner is very important. Okay, that then only you will understand the inner boundary concept and the outer boundary concept of the hole and the shaft. Okay, similarly if we understand the outer boundary for the shaft. Okay, so what is the outer boundary for the shaft? Outer boundary of an external feature of size is a worst case boundary generated by the largest feature of size mmc plus the effect of the applicable geometric tolerance and additional tolerance or the bonus tolerance that may apply. Okay, so here we are saying that the geometric tolerance plus. Okay, so in this case outer boundary, if this is the part, let's say, okay, if this is the part and we are talking about the outer boundary. Okay, so it is mmc, the biggest hole, plus the geometric tolerance value. So we are talking about this size. Okay, so this is the actual mating envelope. Okay, so this is the related actual mating envelope. Okay, so you have to learn these things, outer boundary and inner boundary. Okay, so outer boundary for the internal feature of size will be the outer boundary for the internal feature of size will be the LMC plus geometric tolerance value, and outer boundary for the external feature of size will be MMC plus geometric tolerance value. Okay, now we will understand about the virtual condition. Okay, so before starting the virtual condition, we will understand this concept with the help of example. Okay, so in this case, you will see with the RFS concept, we will understand, okay, for the external feature of size, okay, outer boundary for external feature of size, which we have already understand. Okay, so outer boundary for external feature of size. So let's say the part is being created with the maximum material condition. So for external feature of size, this is MMC and this is LMC. Okay, so for external feature of size for shaft, if the center is at center, so this is the tolerance zone. Okay, so this is the 0.1 dia tolerance zone, TZ. Okay, so tolerance zone we have. Now, if the part is manufactured with the extreme conditions, let's say the center is over here, center is over here, here and here. With the extreme conditions, if the part is manufactured, so this is the extreme condition of the part. Okay, so if this shaft is going to be assembled with the hole, Okay, let's say this is another part and this is the hole. If the shaft needs to be get assembled with this hole, this shaft is going to be assembled with this hole. So what will be the size of this shaft? The maximum size of the hole should be 40.6. Okay, so here outer boundary of the shaft will be maximum material condition plus geometric tolerance value over here. So 40.5 is the size plus geometric tolerance value 0.1. So we get over here 40.6. So the minimum diameter of the hole should be at least dia 40.6. Then only this shaft will going to assembled with the hole. This is hole part 2, and this shaft is going to be only assembled with this hole if the size of the hole will be at least 40.6. Okay, because the extreme manufacturing of this shaft can be at dia 40.6. So this is the outer boundary. Okay, so outer boundary of the shaft will be 40.6. So this is the outer boundary. Okay, and this is the condition of actual mating envelope, related actual mating envelope. If you do not get understand, go back and see that video again, so you will get understanding in a detailed manner. Okay, so we are not understanding the concept of actual minimum material envelope. We are only understanding the concept of outer boundary for the actual mating envelope. Okay, so that's why it is important. Now we will understand about the virtual condition. Okay, so virtual condition is a very important. Okay, so in this case you can understand that the virtual condition, what is virtual condition? I've already told you, it is the worst case condition. Okay, the a fixed size boundary generated by the collective effect of the considered feature of size specified at MMC and LMC. Okay, so virtual condition we calculate for MMC condition and LMC condition. Okay, and the geometric tolerance for the material condition, for that material condition. So in this you will understand that we have four concepts. Okay, four concepts we have for virtual condition. MMC, maximum material concept for internal feature of size for hole. LMC concept for internal feature of size for hole. MMC for external feature of size for shaft or pin, and LMC concept for external feature of size for a pin. Okay, so MMC for hole, LMC for hole, MMC for pin, and LMC for pin. So these are the four concepts one by one we are going to understand in this virtual condition. Virtual condition can be established for a part, okay, for internal feature of size at MMC. So this is the first concept. So we can establish a virtual condition for four concepts. I have already told you, we can take the first concept over here. MMC concept applied to an internal feature of size for hole. Okay, so for hole we are going to understand. So for hole 40.1 is the maximum material condition and 40.5 is the least material condition. So these are the limit of sizes. Okay, and the positional tolerance is applied at maximum material condition. Okay, so here if the it is applied maximum material condition, so 40.1 is the max MMC for hole and 0.1 is the geometric tolerance value. Okay, so virtual condition is the worst case condition. Here is equal to the inner boundary is equal to the MMC minus geometric tolerance value. Okay, so 40.1 minus 0.1, so 40 mm we are having here virtual condition. Okay, so dia 40 we are having the virtual condition. Now the part is manufactured at, so we are having this tolerance zone. Okay, so dia 0.1 is the tolerance zone we have, and the part is manufactured at maximum material condition. Okay, now we have extreme conditions. Okay, so 40.1. So all the four conditions you can see that the hole is manufactured with the size this. Okay, so now you can see, now this is the inner boundary. Okay, so now you can see. Okay, so inner boundary here is the smallest shaft that can enter inside this hole. So inner boundary is equal to, why we are calculating the inner boundary? Because we have to calculate the size of the shaft is the dia 40 mm. So 40 mm pin or the shaft will enter into this hole. Okay, so that's why we are calculating the inner boundary of this hole. Okay, so in this case, I have already told you that the virtual condition is equal to the inner boundary. Virtual condition is equal to the inner boundary. Inner boundary, the formula of inner boundary, I have already told you, MMC minus geometric tolerance value. MMC over here is 40.1 minus 0.1, which is geometric tolerance value, and 40 mm dia is the inner boundary or the virtual condition. Okay, so 40 mm dia of pin will can enter into this hole. Okay, so this is the size of the pin that can enter into this hole. Okay, so this is the MMC concept for the internal feature of size. Now we will understand the LMC concept for the internal feature of size. Okay, so LMC concept for internal feature, in this case also, this is MMC and this is LMC. Least material condition, maximum material condition. Okay, so but here the modifier is of least material condition. So we will take the least material condition, which is 40.5. Okay, so in this case, the 40.5 will be the least material condition, is the largest hole. Okay, so this is the largest hole. And in this case, we will calculate the, for least material condition. First of all, this is the size. This is the least material condition. This is the size of the hole. And for this, the tolerance zone is of 0.1 only. This is the tolerance zone we have. For extreme conditions, when the part is manufactured at 40.5 at extreme condition. Okay. So this is the extreme condition we have, that the part is manufactured. Okay. So in this case, the virtual condition will be the outer boundary. Okay. So virtual condition will be the outer boundary over here, which is the least material condition plus geometric tolerance value. Okay. So outer boundary for the whole, you can see this green circle. This circle shows which is of outer boundary, which is of dia 40.6. So in this case, least material condition is dia 40.5 plus dia 0.1, which is geometric tolerance value. So this is the 40.6. Okay. So this is also the virtual condition is equal to the outer boundary. Okay. And this outer boundary, we have already known that this outer boundary is a related actual minimum material envelope. And this is the imaginary envelope because this is inside the material. Okay. So this is always this outer boundary of the whole. Okay. So this is the outer boundary of the whole, which is inside the material. Okay. So that's why it is called the imaginary boundary. It is also called the imaginary boundary, and that's this is the imaginary boundary. Okay, so because this is inside the hole, because in this case the hole will be much more bigger. Okay, so this is the worst case condition or the outer boundary in this case. Okay, now we will understand the concept for the MMC condition for the external feature of size. Okay, so now we will understand the MMC concept for the external feature of size. So now you can see that for external feature for pin, so this is for pin. So this is the MMC 40.5 and this is the LMC. Okay. So if the part is manufactured at maximum material condition, because the modifier we have used here over is MMC. Okay. So if the part is manufactured at maximum material condition, so MMC maximum material condition is dia 40.5. We have tolerance zone. This is the circle denotes the tolerance zone, which is of dia 0.1 tolerance zone. Now we calculate the worst case condition. Okay, so the extreme conditions for this 40.5. Okay, so these are the worst case condition. Okay, so we are calculating the MMC concept for external feature of size. Okay, so in this case, what will be the worst case condition? What will be the virtual condition for this? So virtual condition is equal to the outer boundary of this shaft. Okay. For the maximum material condition, the worst case condition will be the outer boundary of the shaft will be 40.6. So this green circle is showing the outer boundary of this shaft. Okay. Which is outer boundary. In this case, maximum material condition plus geometric tolerance value. Okay. So maximum material condition is 40.5 and the geometric tolerance value is of 0.1, which is dia 40.6. Okay. So virtual condition is equal to the outer boundary, which is 40.6 for the shaft. Okay. So this is the actual mating envelope. Actual mating envelope. Now, if this shaft is going to enter with the hole, let's say this is the part 2 with the hole. This is a hole. Okay. So the diameter of the hole should be minimum diameter of the hole should be 40.6. Okay. Then only this shaft will enter into this hole. Okay. So that's why this is we are calculating the outer boundary for this shaft. Okay. So that it can assemble with the mating part. In this case, it is hole. Okay. So this is the condition for the MMC concept for the external feature of size for the shaft. Now we will understand the LMC concept for the external feature of size. Okay. LMC concept for the external feature of size for shaft. Now, again, in this example for shaft, this is MMC and this is LMC. But this here in the feature control frame, we have used the modifier which is LMC. Okay. So the dia 40.1 will be the LMC. Least material condition will be LMC is equal to dia 40.1. Okay. In this case also, if we see the tolerance zone, so dia 0.1 is the tolerance zone. If the part again manufactured at worst extreme boundaries, let's say this is the center, this is the center, this is the center, this is the center. So if the part is manufactured with worst case or the extreme conditions, what will happen? In this case, it will be the inner boundary. Okay, so inner boundary will be the size, but virtual condition. Okay, so in this case, you can see this is the virtual condition. So virtual condition is equal to the inner boundary for LMC. LMC concept, the external feature of size or shaft will be the inner boundary. For LMC, minus geometric tolerance value, which is 40.1 minus 0.1, which is 40 dia. Okay. So means this is the inside this shaft. Okay. So again, inside the material, when the concept is inside the material, this is inside the part, inside the material. Okay. So this is, you can see inside the material. So whenever it is inside the material, it is imaginary. Okay. Imaginary virtual condition. So it is imaginary and actual minimum material envelope. These concepts are very important. Okay. If you don't understand, do repeat these videos and try to understand these concepts, because this condition, in this condition, these are the virtual conditions which you have to remember and have to learn in a very detailed manner. Okay. Now, so this is the chart. Okay. So this is the chart which I have already discussed. We have discussed with the feature of size. Okay. So the part specification with the feature of size with no GD&T specified for the internal feature of size, for the external feature of size. So for inner, when this is the condition for internal feature of size and external feature of size. So inner boundary is the maximum material condition and outer boundary is the maximum material condition. Okay. Now feature of size with GD&T specified at RFS. Okay. So for internal feature of size, external feature of size at RFS, inner boundary is equal to the maximum material condition minus geometric tolerance value, and the outer boundary for external feature of size, outer boundary is the maximum material condition for plus geometric tolerance value. Okay. When feature of size with GD&T specified at MMC. So MMC for internal feature of size and MMC for external feature of size. So virtual condition is equal to inner boundary equals to MMC minus geometric tolerance value. Okay. For external feature of size, virtual condition will be the outer boundary is equal to MMC plus geometric tolerance value. Similarly for LMC, for internal feature of size and external feature of size, virtual condition is equal to for internal feature of size is equal to outer boundary LMC plus geometric tolerance value, and virtual condition will be for external feature of size will be inner boundary is equal to the LMC minus geometric tolerance value. Okay. So these are the some of the formulas for the worst case condition. So these are the worst case boundaries which is equal to. Okay. So these are the terminologies which you should be learning, and this is very very important. Okay. So these are the some of the formulas which we understand. Okay. And with the help of these boundaries, we design the functional gauges. Okay. So we only design the functional gauges with the help of these dimensions. Okay. So for external feature of size, we have some virtual condition for both the internal feature of size and external feature of size is same. Okay. Now we understand. So again, if we take an example, similar example as we have taken at the starting of this session. Okay. So again, if we take the same example as we have taken in the starting of this session. Okay. So this is the example. So in this example, you can see that if we need to assemble the whole, this is the whole or the internal feature of size, and this is the pin, which is the external feature of size. Okay. So what will be the sizes? So in this case, the maximum material condition of the hole is mmc is 40.1. Okay. And the least material condition of the hole is 40.5. Okay. But in this case, now I have changed the sizes because we have to ensure the assembly. Okay. So in this condition, the least material condition of the hole is 39.5, and the maximum material condition of the hole is 39.5. So if we go with the worst case condition, okay, so the worst case condition this hole can manufacture is the 40.1, which is the maximum material condition of the hole, and the geometric tolerance value of 0.1 at mmc, because mmc modifier we have used over here. So what will be the worst case condition? The worst case condition will be 40.1 minus 0.1. Okay, so the smallest hole. So the smallest hole will be the worst case condition. So mm's worst case scenario for this hole will be, worst case boundary will be dia 40 mm. Okay. Now, similarly, if we go with the shaft, so 39.9 is the maximum material condition because mmc modifier we have used over here. So 39.9 is the maximum material condition. 0.1 is the geometric tolerance value, and worst case boundary will be the biggest size of the shaft. Okay, the largest side of the shaft will be the outer boundary. Okay, so 39.9 plus 0.1. So dia 40 mm. So if the worst case boundary for hole is 40 mm and the shaft is 40 mm, so these both part can assemble with one another. Okay, so these both part can assemble. Okay, so this is how designers have to ensure and give such dimensions that the part at maximum material conditions with the worst case boundary can assemble with one another. Okay, so here the worst case boundary for hole is dia 40 mm, and worst case boundary for shaft is dia 40 mm. Okay, so that's why we can assemble hole with pin. Okay, so this is how we have to take the dimensions. So this is all with the virtual conditions. We will, in the next discussion, we will be discussing the next topic, which is the about the resultant condition. Thank you all of you.